The motivation for his prize, the Crafoord Prize, is given here for fundamental contributions to our understanding of how aerosol particles and other climate pollutants influence the atmospheric energy balance and the Earth system. This motivation was carefully crafted by the Crafoord Committee of the Academy of Sciences here. Ramanathan was born in a village near Madurai in southern India, a little bit south of Madras, Chennai, in 1944, so he's now 81 years old, if I counted correctly. He is educated first in India. He got his MSc at the Indian Institute for Science in Bangalore in engineering science. He moved then to the United States and got his PhD at State University of New York at Stony Brook on planetary atmospheres. So this is a summary of his career positions. He started actually as an engineer. He's interesting at the refrigeration industries in India. So that's where he came in contact with the CFC that later was one of his research interests. He worked at Boulder at the National Center for Atmospheric Research. He moved to NASA. He was employed by NASA already in 1979 as a principal investigator of a large radiation experiment called the Earth Radiation Budget Experiment. I'll talk about that a little bit later. He's also spent 5 years as a professor in the University of Chicago. And since then, he's now based at the Scripps Institution of Oceanography in San Diego, the University of California. He's also an adjunct professor at Cornell University. He's an elected member of several academies. I just listed a few here. The US National Academy of Sciences, the Pontifical Academy of Sciences, and of course, the Royal Swedish Academy of Sciences. Numerous awards. He has been awarded with numerous awards. One could mention more than these. Bois Ballot, I don't know how to pronounce that. Bois Ballot. The Rossby Research Medal, the Tyler Prize, the Blue Planet Prize, the Tank Prize, the Volvo Environment Prize, I forgot to put in this list, and more lately, the Grand Medaille from French Academy of Sciences last year. And now, finally, the Crafoord Prize here. Publications, he's written several hundreds of scientific papers, co-authors and authors. They're cited altogether nearly 90,000 times. And it's interesting to note that it's not just one or two papers that are sort of brings in most of these citations, but has actually a lot of papers with more than 1,000 citations. So he has this, I think, shows that he has a very broad impact on the scientific community. Here I've listed what I think are the most fundamental scientific achievements of Ramanathan. I just first mentioned them: the greenhouse effect due to CFC, detecting climate change due to increasing CO2, lead of NASA's Earth Radiation Budget Experiment, observational determination of greenhouse effect, and with the Indian Ocean experiments co-led with Paul Crutzen, and finally modeling human natural interactions with implications for global warming. Not just natural interactions, but human natural interactions. I will not mention these in detail because I'm sure he will talk about them himself. But the ones that I've marked with red, I will make some few comments. Soon after, Roland and Molina had estimated that emissions of CFCs, chlorofluorocarbons, could lead to a thinning of the ozone layer. Ramanathan started to look into their absorption of long-wave radiation. To the surprise of all of us, he found that despite their very low concentrations in the atmosphere, their very strong absorption of long-wave compared to CO2, about 10,000 times more stronger than on a molecular basis. The chlorofluorocarbon gases cause a greenhouse warming almost as large as that of CO2. I think this was a very remarkable result. That was unexpected. The second red item here is Earth radiation budget experiments. It was a very ambitious experiment that lasted for several years, based on mainly on satellite observations, but also surface measurements of radiation. They were able in this experiment to measure most of the major fluxes in the atmosphere, above clouds, under clouds, short wave and long wave, and they came to the conclusion that the cooling effect of clouds, I mean, the clouds reflect some light to space and thereby cool the surface relatively. On the other hand, they also absorb long-wave radiation from the surface, thereby causing a greenhouse effect. But nobody had before been able to estimate which one is the dominant effect, the cooling or the warming. And from out of this ambitious radiation budget experiment was a clear conclusion that the albedo, the cooling effect, dominated the warming by almost a factor of 2. So cold clouds on averaged over the globe, averaged over different types of clouds, they cool the planet. And that's an important conclusion. The third red item here, the Indian Ocean experiment, is a very ambitious, also very ambitious field campaign run for a couple of years, mainly over India and the Indian Ocean, all the way out to the Maldives, where one could follow polluted air from the continent, reaching all the way out to the Maldives and polluting and potentially affecting the climate far away from the pollution sources. And this was a really new perspective on pollution. Man could see that it spreads over large distances and affects climate. After that, there was another project also initiated by basically Ramanathan, and the atmospheric brown cloud study, in which we were trying to determine the physical and chemical characteristics of the particles that causes. And main results of this project was that black carbon, the soot basically in this pollution, it absorbs heat and thereby warms the atmosphere. And so it's a climate agent. It also dims, it shields surface from sunlight, which is a problem because of it for food, growth of food. And also, of course, these clouds have when they're in an urban area, they have a strong health effect. Now, in this connection, the concepts of short-lived climate pollutants was created, was sort of introduced, and now as a final, the wider impact of Ramanathan knowledge, society, and policy action. Here, in the middle, you see the Climate and Clean Air Coalition was formed in 2012, and with US and Sweden as key grounding fathers of this organization. And that program, that organization collects, or brings in not only governments, but also non-governmental organizations, businesses, and other all kinds of partners to help reduction, to stimulate reduction of short-lived climate pollutants. The most important short-lived climate pollutants, actually, you can say, is soot, black carbon, that heats the atmosphere, and sulfates that reflect sunlight, thereby cooling its surface. So we have a sort of competition, and here also between the soot absorption and the sulfate reflection in the clouds. Let's see, Pope. I'll come to the Pope here. As a member of the Pontifical Academy of Sciences, Ramanathan helped organize a major meeting on climate change resilience with Pope Francis as a chair, I think. And that's illustrated with this picture here. So I'll conclude by showing. No, this one more here, yes, sorry. This is a very important program initiated and run by the University of California with Ramanathan as a primus motor. And it is it's a training program aiming mainly at young people. So he has engaged himself a lot in this program lately, bending the curve. So here is my final slide. This is my personal view on what makes Ramanathan a true pioneer and world leader in climate change science, which I think he is really. The breadth and depth of his scientific knowledge and his many fundamental scientific contributions, publications. His ability to see the big picture, to summarize and to synthesize, very important. His ability to build bridges, not only between different natural science groups, but also with social scientists and policymakers. I think this is amazing how successful he has been there. Finally, a very personal comment from me, his friendly and humble attitude towards his fellow human beings. Congratulations on the Crafoord Award, Ram.
Thank you very much, Henning, for this. And now to the laureate himself. Welcome, Veerabhadran Ramanathan.
Thank you. Thank you.
Please.
Thank you very much, Professor Henning Rodhe. As I was listening to you, my only thought was, there is nothing I can say which it can improve on it. Maybe I should keep quiet, but I did commit to giving a 45-minute lecture, so I'll do that. I want to first start off thanking, I am really deeply, deeply honored by this recognition. My sincere thanks to the Royal Society of Academy of Sciences, the Crafoord Foundation, we met them at the Lund 2 days ago, and the Crafoord Committee, which chose me as this year's laureate. also comes at a critical time for me. I'll explain it towards the end. There are many here who have pioneered many discoveries in the climate change. I think we will hear some of them after my talk. These are really challenging times for climate scientists like me who have been working on this problem for decades. This is my 56th year in climate change science, so 6 decades. And we have witnessed, just not me, many here, our predictions come true one by one. Yet the gigantic efforts we need to stop the crises from worsening have not achieved the needed success. However, I'm confident success is still within our reach. What do I mean by success? If you let this go to its ultimate end over this century, billions would suffer. So for me, success is not really just cutting down emissions, this and that. Success should be measured in how many people we can save and protect. And that's what I mentioned to Pope Francis. There are 3 billion poor who have suffered 75% of the losses so far from climate extremes. But their contribution is minimal, just 5 to 10%. So what we need is a new approach. We can have discussions why we are not succeeding as fast as we need to, but we need a new approach. I'm going to touch on that. But what I'm going to spend my time today is talk to you about the science of climate change. Show you by actual data that we have a robust theory of climate change based on sound fundamental principles of physics, quantum mechanics, thermodynamics, chemistry, and even biology. The speakers just in the audience cover all these disciplines. So, and this theory has passed crucial tests. I'm going to describe some of that to you. I'm going to call this the energy balance theory of climate change. If you like this title, you shouldn't give me the credit. As Professor Henning Rodhe said, I've been fortunate to receive many awards, but this is the first award which mentions energy balance. And that's what I see my work as, on energy balance. So I want to congratulate the committee for bringing this to the fore. But the contribution to this energy balance theory of climate change started, I think, in fact, in this hall. It's Professor Svante Arrhenius who first employed the principles of energy balance to figure out how CO2 is going to heat the climate. Okay, so it's at least 150 years old. What is remarkable about this theory is that it requires just 3 variables. Climate is a complex phenomenon. The forests influence the climate. We human beings, animals, influence the climate, but it can be captured under 3 variables. So in testing this theory, that's what I spent my life on. I'm a skeptic. I don't believe models. Even theories, I'm very skeptical unless I can show them with data. That's what I spent my life on, using observations to test the theory. I followed this framework: detecting a change, attribution, give a causal factor for that change, and then use the 2, detection, attribution, to advance the theory and then make predictions. So the ultimate test is prediction. In the spirit of Einstein's relativity theory, it was Eddington who did that decisive experiment to prove his theory of bending light. We don't have such a proof. We have many proofs to look into this. So using this theory and this framework, what I would like to show is that the climate system is predictable on at least a 10 to 20 year time scale. Why not longer than that? The human behavior fundamentally is unpredictable beyond, so it shows up. The physical system, like oceans, also dominate the inertia. So let us start with a holistic view of the planet. I decided to start with this slide. This was taken just a few months ago from the Artemis crew. We have a legendary astronaut here in our audience, Mr. Scott Radinsky. So I'm sure he's going to talk to us day after tomorrow. Our planet is called the Goldilocks planet. Why? It's at the right temperature for us humans to thrive. And the astronomers think it's at the right temperature because it's at the right distance from the sun. The Venus is too close, it's 400 degrees hot. Mars is too far. But I'll show you there are many more things than just the distance to make the planet habitable. Why Goldilocks has her porridge at the correct temperature. It's just not the distance, it's many more, and we control all of them, unfortunately. So let's talk, remember I said detection, attribution, prediction. So let me start with the detection framework. The left side shows temperature of the planet averaged over the entire globe. There are billions and billions of observations going to this, okay? From ships, from buoys, from surface stations, from balloons, and now from the 80s onwards from satellites. What we see here is for the first 50 years of the 20th century, the planet was gradually warming. Then it was interrupted. Just before the 1950s, it went into a cooling phase. I entered this field in 1973. At that time, the planet was still cooling. And my colleagues used to think I'm crazy to think about global warming. Okay, there was even talked about ice age. And then you see the warming picked up mid-1980s, and it's going nonstop. What is most disturbing, and I'm going to talk to you about this, last 15 years, it has accelerated. The warming rate, in fact, Gunnar, hopefully will talk about this. He has done a lot of work on this, Professor Gunnar Meyer from Oslo. On the right-hand side, what you see is the temperature of 2025, okay, just 1 year, but it's showing how the warming has increased compared with the temperatures of the mid-50s. And what you see, just 3 general features. The land is warming more than the ocean. The northern hemisphere is warming more than the southern hemisphere. And the polar region warming a lot more, both in the Antarctic and Arctic. All of this was predicted by the theory. In 1960s, 1970s, after Arrhenius, I would think the most decisive work pointed us in the right direction was Suki Manabe's modeling work. And he got the Nobel Prize 3-4 years ago. So I'm going to talk to you about all this. None of this comes as a surprise to us. What comes as a surprise to me and many of my colleagues is the acceleration of the warming in the last 15 years. None of us predicted that, and I'll get into that. So now the attribution. What did we think was causing this warming? The increase in the carbon dioxide. Similar observations, kindly forgive me, I'm going to brag about my institution, Scripps Institution of Oceanography. We have the Vice Chancellor of the university here, Professor Meena Wadhwa. David Keeling, my colleague there, he started these measurements, and you show it's just increasing year after year after year. Okay? Since the time he started, it was 300 parts per million. Now it's 440, almost 40% increase. Okay? So what is the source? All of us sitting here, and our parents, our grandparents. Cars, buildings, cement, everything we do. But we shouldn't forget that increased our living conditions. Okay, so I'm not going to say they were all bad. No one knew this. It was inadvertent, okay? So what happens? For example, I drove today, and what is the CO2 I emitted? Where does it go to? This is supposed to be a video. I think it's not working. Is that correct? All right. So what you would have seen, this is air at 5 kilometers. If the video was working, the clock is ticking on the left-hand side, you will see air moving. For example, air from China, in less than 2 weeks, comes to San Diego, California. I use drones to directly, remember, I don't trust anything the models do, with all apologies to my fellow modelers here. But I'll show you concluding how the models are remarkable in making good predictions. In any case, so while I'm smelling the air from China 2 weeks, the air I emit in San Diego, you Europeans would be smelling the air in 5 to 6 days. And emissions from Europe would go to China. The main thing is that we are never ever going to solve this problem by pointing fingers at each other. We are all doing this. We are interconnected. So emissions anywhere is warming everywhere. And this movie shows spectacularly how biomass burning in Amazon goes straight into the Antarctic in less than 6 days. So that's the key thing. If anything, we need to convey to our politicians and leaders is that. So what happens then, the CO2 covers the entire planet like a blanket. The greenhouse effect, I used to use that too. It's scientifically has problems. I like the word blanket. So if you see how a blanket warms you in a cold winter night, the blanket doesn't give you any heat. It has no heat source. It just traps your body heat. That's exactly how the CO2 blanket works. It traps the infrared heat given off by the oceans and by the land. So this is the theory of climate and climate change. The 3 components, I call it Earth energy balance. I have to say, I stole this from the citation of the Crafoord Foundation. Thank you so much. It was just, I had never thought of my work in that context. And who pointed out to me, I think Ellen called me when we were having a lunch in a Thai restaurant, me and my wife caught on. Energy balance, that is what you've been doing all along. So in any case, it is a sum of 3 components. Incoming sunlight, not all of that is absorbed by the planet. It reflects back. When I got into the field, we didn't know how much it was reflecting. It was all from models. And then that net incoming sunlight heats the planet. And the planet gives off this heat as infrared. And this infrared escapes to space. It goes on till what comes in as sunlight is balanced as reflected sunlight and emitted infrared. Okay? This was the perfect energy balance we were on till Mr. James Watt invented his steam engine. Okay? And then we went into energy imbalance. We were thickening the blanket, so the emitted infrared radiation was blanketed. So there was energy imbalance. So what does the planet do? The ocean heats up in response, tries to give off this radiation as infrared, EIR, all right, and restores the balance. So that is the theory in a nutshell. So when we went from energy balance, as Mr. James Watt reached his 20s and started the invention, we went to energy imbalance. And then the planet restores that imbalance by the 3rd equation. The rate of change of temperature is equal to EEI. This is the equation Mr. Arrhenius, the famous Swedish chemist, started, except he did his balance at the surface because there was no data those days. Later we learned we have to do that balance at the top of the atmosphere. Okay? So when I got into this field in 1973, I read this, and there was only model results. I happened to be at NASA sitting next to one of the brilliant engineers. And he wanted to do a climate satellite. Over a period of several lunches and coffees, I bought the lunch and coffee. I persuaded him I am his man, because there was no one in NASA at that time that worked on climate change. So we designed the Earth radiation budget satellite. There were several of us got into the picture. It was launched in 1984 on the Space Shuttle Challenger, and you see there the astronaut Kathy Sullivan. In that mission, first time 2 women astronauts, Sally Ride. Sally later came to Scripps and she recruited me back. So it's a series of accidents like that is what made my career. So you can see that our instrument was just being launched, okay? But that it took us 10 years to launch it from the point of design. And believe it or not, it cost $250 $250 million just to design that instrument, okay? And I was fortunate. I teamed up with, those are all NASA scientists, Bruce Barkstrom, Ed Harrison. And NASA wanted me to lead that mission. My wife, who was sitting here, and my advisor both said, you won't be a good manager. Don't take this position. So fortunately, I listened to them. I got to work on the science. So I'm going to show you how we used this experiment to figure out how the Earth's climate was working in parallel to the models. We'll always go back and forth. And what I did was what I call the twin Earth idea. I'll talk to you about this. We figured out the greenhouse effect. The dominant greenhouse gas, or the blanket, is not carbon dioxide, it's water vapor. Okay? Then comes carbon dioxide. Then my work on the CFCs, which Henning talked about, started a whole branch of other gases, clouds, aerosols, and then climate feedbacks. So what we did was figured out what was the Earth energy budget, how was it changing as we dump more blanket gases, and then how would the system respond, all right? So what is the twin planet idea? At that time, everyone knew clouds was the dominant contributor. This was Suki Manabe's modeling work, okay? And without the models, we couldn't have designed these experiments. The models is the ones who helps refine the theory, and then we go to the data to refine the models, okay? So the first thing we measured was what was coming in, that 340 watts per meter squared, that's 100%. The Earth was reflecting 30%. If I was not talking to a general audience, I would use the number 29. I didn't want to condensely rounded it off, okay? So then it hits the planet, and then the Earth gives off that energy as infrared. The Earth emitted, it's called, meteorologists call it long wavelengths, okay? So we determined that. And this was the first time I convinced that engineer. Before that, NASA had sent this Earth, but they were not calibrated. I told them it's worthless without calibration. So we had an inside calibration, and then we would turn the satellite belly up to look at the moon and calibrate with the moon's temperature, okay? What at that time NASA engineers were doing were a whole lab in New York, over 50 scientists, they were trying to measure each cloud, okay? I knew it was futile because clouds are turbulent. And you know what Einstein said about turbulence? I cracked this joke in Lund. To his biographer, he said, you asked him, are you afraid to die? And Einstein said, yes. And the biographer thought he's got something exciting, Einstein being scared of dying. And he asked him why. Einstein said, I'm afraid I'll find out even God doesn't understand turbulence. So I said, we can't be taking our instrument and looking at each cloud, create a twin Earth. The clear sky, you see the holes in the clear sky? Measure the clear sky flux, because clear skies are more homogeneous than cloudy skies. And then measure the whole Earth, cloudy sky, difference the two to get the effect of clouds, okay? So the first thing I want to talk about is, you said a natural blanket. Okay, why is Goldilocks having her porridge at the right temperature? You see that we measured every clear sky in the planet for 5 years so that we get a good average, mainly over the oceans. There's a complication with the land. I'm not going to get into it now. So that's what the ocean is emitting. This is from the ocean surface temperatures, buoys. The ocean is emitting 400 watts to get rid of 268. The rest is trapped by the blanket. That trapping effect of 130 watts is coming mainly from water vapor, about 2/3 of it. So the dominant greenhouse gas is not CO2, is not CFCs, it's water vapor. Okay? If that greenhouse effect, instead of 131, let's say it was just 120, just 10 watts, Goldilocks would have a frozen porridge, not at the right temperature. The planet would be frozen. Okay, if it was 140, it would be ice-free. All right, that's about 3 times the CO2. Why did nature settle on this? I'm still thinking about that. Okay, just the blanket thickness was just perfect to maintain the planet's temperature at 15 degrees. So now comes the clouds, and I show them my twin planet. Every time there is a hole in the cloud, I look at the radiometer data. So I created a clear sky planet, then a cloudy planet, and the difference the two. And let's see what that showed. You see the scanning radiometers those were the radiometers go back and forth across as the satellite was going this way. So what did we find? The clouds, I used to call it schizophrenic. They don't know whether to cool or heat the planet. They had a blanket. They will trap the infrared, and that's what I showed. You see the massive amount of trapping happening in the tropics. These are the deep cumulonimbus clouds with cirrus anvils. Okay, but what was amazing is that the trapping was exactly equal to how much sunlight they were reflecting. There is no reason for that. The reflection depends on the size distribution of cloud drops, okay? Whereas the blanket effect doesn't care about the size of the cloud drops. So there's no reason it has to come to this way. So when I added the two, what you see in the tropics is that they're behaving as if there are no clouds. Blue is zero effect, okay? Most of the cooling, you see the 18 watts is the difference between the two, is coming from clouds in the extratropics. These are the clouds when you fly from Stockholm, go to New York, you see nothing but white sheet, right? It's those clouds. They are the ones cooling. And in fact, Frida Bender, professor at Stockholm here, she was in my lab, and she showed these clouds are retreating, these cold clouds. She stopped communicating with me. I'm going to find out from her today what's happening to them. They're still retreating. All right? So for example, if this net effect instead of 18, minus 18, it was 22, the planet would be too cold, almost ice covered. So everything depends on this, how these things settled. A natural system, so delicately balanced. So if I spend 3+ nights, it's that. We have not understood yet why it's 18, why it's not 25, why it's not 10. Okay, there's no theory for it. So now I'm going to take you to climate change science. This was, again, I was still at NASA. My daytime job was to look at the rocket effect on climate change. So without telling my supervisor, I was working on this in the nighttime, one evening. And my wife still remembers that. I'll come home, have a quick dinner, and take her to an ice cream place. That was her weakness. It still is her weakness. So she'll forgive me for working from 7 to 12. And we stumbled on this, that the CFCs just because of their quantum mechanics, they were 10,000 times more potent than CO2. Okay? That's where they brought in chemistry as a central player in climate change. I'm going to, those of you who are not chemists, you can close your eyes for this slide. I just want to explain why it's so effective. What you see on the top, this is data directly over the Pacific Ocean. So the surface, that's what the surface is radiating. If you go outside and I put a radiometer, the radiation coming from your body will be very close to this curve. Okay? All solid bodies, black bodies, emit our human surface, we emit infrared. But what escapes to space, this was not the instrument we had. This is a fantastic instrument designed by scientists, astronomers who are working on Venus. You see in this wavelength, the CO2 blanket is so massive, nothing escapes. So that's the, you think of the black area, the shaded area, as the thickness of the blanket, and it varies with wavelengths, okay? But in the region between 8 to 12 microns, the background atmosphere, neither water vapor, nor CO2, nor ozone absorbs. We used to call them atmospheric window. So for example, if you stood out, the radiation coming from you could be measured, 80% escapes to space. So if I want to spy on people, I would make a radiometer 8 to 10 micron. I can measure each one of you, okay? And that is where the CFCs are absorbing. Why in this wavelengths they are absorbing and why they are so potent is because they're asymmetric. They have permanent dipole moments. Any jiggling, they will start radiating, okay? All that combined to make them 10,000 times more potent. In fact, after my work in this, a science fiction writer wrote, if you want to heat up Mars, before colonize Mars, send CFCs. They'll heat up the planet in no time, okay? I'm not advocating it by any way. So that was my entry into climate change. Then the addition of CFCs, then other scientists proposed other compounds, methane, nitrous oxide. There's a whole host of them now, okay? So I decided we should be seeing this warming right away because we have doubled the importance of the problem. So I teamed up with the famous, meteorologist, Roland Madden. There's an oscillation named after him called Madden-Julian oscillation. So Madden was, of course, next door to me. I always trap my office partners. So I told Roland, hey, why don't you do something more useful than what you're doing? Tell me, he still tells that story. And he had just been recognized by the US government with the name Madden-Julian oscillation. And I told him, do something more useful than that. So we teamed up and we did what's called a statistical dynamical study. When are we going to see this warming? How soon? I did the modeling using the energy balance theory. I was testing the theory. Constantly, I was only doing testing that theory. So we published this paper in 1980 when the planet was still cooling, and the cooling just ended, and we said, if this theory is correct, we should detect the warming by 2000. Remember, what we are talking about, what you see, those jiggles, they're all noise, weather noise, 1 year, El Nino, this and that. We said, when will the warming will be 2 sigma, 5% probability of being wrong. And we came with the year 2000, and that's when the warming really far exceeded background noise. So I think of this, one of the first predictions using the energy balance theory, which was proven. Okay, but one test doesn't prove much. You need multiples of stuff. What happened was, although we succeeded in predicting the theory, the warming we were predicting was much larger, twice as large. The planet should have heated a lot more. It wasn't. And so is it something where either the theory is wrong or exaggerating, or something was masking the warming, okay? That is when I started reading papers by Henning, Rodhe, and other aerosol chemists. They were working on the aerosols for the acid rain problem. But a few scientists, one is Charlson at UW and a few others were saying, no, they were also reflecting sunlight. Why is the sun hazy when you have air pollution? They're scattering light. So they're scattering light towards you, and they're also scattering light back to space, okay? So we wanted to measure the masking effect, and several here participated in a big way. Kim Prather, Gustafsson, and all on the aerosol, on the chemistry side. My focus was on only one question. Were the aerosols reflecting sunlight? If so, how much? And then we work with the chemist to tell us what is doing that, okay? So we had 6 aircraft. I think Joost Lelyfeld, who is here, we are going to hear from him, was the major lead in linking the air pollution part to the what we were observing. Okay, it was a Dutch aircraft. I think thanks to Paul Crutzen's influence, I can't take credit for attracting all this engineers. It was Paul, and I think for us, he was the god. I never asked him if he knew about turbulence. I feel I should have asked Paul if he understood turbulence. He was such a figure, huge figure, and I personally, probably the most brilliant scientist I had met in my life. So we did this experiment, and what we, you see the massive clouds coming from the Indian region? That was the air pollution part, picked up by satellite. And we were on the Maldives. One branch of the pollution will go there, one will come here. So what we found, we had instruments, and on the far right side is the observatory or the Maldives. So the IRBI, every time it goes over Maldives, that's where our headquarters was, we'll find out the reflection. And then the aerosol chemists like Kim and NASA scientists told us how much aerosols were there. So we would plot the reflected thing we measure against what the surface measurement said is that how much aerosol is in the column, how much in the surface, and you see the monotonic decrease. Almost 25 watts were reflected back to space when the aerosol, the optical depth is a technical thing. Just think of it as physical thickness multiplied by scattering. So there was no question in our mind. And then we did the similar measurements in many other parts, over China, over Korea, and off of US, California, we found a similar signal, okay? Why was this a surprise to us? Because the aerosols not only scatter sunlight, the black carbon in the aerosol was absorbing light, so we didn't know which was dominating, okay? And I think, let me just see. Yeah, what we did was that for every photon reflected back to space, we were missing 3 at the ground. So we thought the other 2 was instrumental errors or something is trapping that. So we designed a UAV, 3 UAVs to fly simultaneously. The top one will measure how much was reflected, the bottom will measure how much is coming through, and the middle one would see where the thing was going up and down. They had to fly within 5 meters of each other. And NASA sent their engineers to us to see figure out how we did this, line them up with 3, one over the other, okay? And we had miniaturized instruments. This work of miniature is not mine. I had the good fortune of some brilliant experimental scientists, Greg Roberts, Craig Corrigan, and Ramanathan from India. They had designed all these instruments, rebuilt it in our lab. So what we found, that shows us altitude, heating. Where was the heating taking place? The aerosol black carbon absorption was not taking place at the surface. So the surface radiometers would miss it. The absorption was taking place above 1 kilometer. And I interpreted as that the surface or recent aerosols that at 1 to 2 kilometers were coming from long distance. So the aerosols needed about 3-4 days to mix into a globular sulfur, nitrate, black carbon. And the models were off by 50%. This is still a huge uncertainty. Kindly don't think I'm claiming we have solved the aerosol problem. There's still uncertainties. And in fact, Orion Gustafsson, I think, I put him in a spot, has the most authoritative statement on what black carbon's doing. I'm looking forward to listening to him. So this is our summary, okay? This is how the Earth energy budget is upset. Carbon dioxide blanket is trapping about 2 watts, and all the other gases 1.7. And the aerosol masking, there's still, again, a lot of uncertainty. My estimate for my group, based on just satellite measurements, no models, is that the net effect of aerosol is the mirrors. Think of the aerosols as mirrors on the blanket, reflecting light. And then, but that mirror is a smoky mirror. That's the dust and the soot. So when you add the 2.3 minus 0.9, the net effect is 1.4 cooling. All right? I'm going to tell you later, I'll show you some figures. That's about 1 degree has been masked warming. So if this data is correct, there is still uncertainty. I don't think, I'm not going to say it's wrong, there is uncertainty. We know the net effect is cooling. That, I think we have proved that. How much cooling, I don't know, but my data suggests 1 degree cooling. That 1.3 watts, if it not be there, the planet would already be close to 2 degree warming. All right? So now I want to quickly go to, we have a rough idea of now how we have changed the planet. We have put the blanket, we put mirrors on the blanket, reflecting light, trying to cool, but then we made the mirrors into smoky mirror, heating. All this mess has to be added up. How would the system going to respond? This is the thing I started because of Arrhenius. Arrhenius said, when the planet warms, the relative humidity will be same. What does that mean? The absolute humidity will increase, okay, exponentially. That is the Clausius-Clapeyron equation. I look for it everywhere, and I found this is all over the oceans. No matter where in the ocean, the Arctic Ocean off of Sweden, or the Pacific Ocean off of San Diego, it follows that curve, the water vapor in the column. And the slope is exactly what's given by Clausius-Clapeyron. So the thermodynamics has a death grip on how much. So why is that a problem? Water vapor is the dominant greenhouse gas. So you're heating the planet, and the planet wants to give off that heat, but in so doing, the water vapor is increasing. So it's trapping more. The planets have to work even harder. How much harder? I'll show you it's 3 times harder. So that doesn't prove anything. Just water vapor is increasing. What we need is the blanket thickness. So we measured the blanket thickness using the twin planet idea. I don't know why many have not caught on to it. This is the way they can find out how the planet is heating up. So what we found is the slope. The greenhouse effect, the blanket is thickening at the rate of 3.53 watts per meter square per degree Kelvin. Okay? Of all the numbers we have generated from my lab, the one which has remained the most obscure, and the one I think is the most important work we've done, is that number. Why is that so important? See, the ocean wants to radiate 5.4 watts every degree warming. But the atmospheric blanket is getting thicker, that's trapping 3.5. Only 2 watts can escape. Okay? If there was no atmosphere, 6 watts would have escaped. What does that mean? I'll come to that. There's one more feedback. This was also done by a graduate student of mine, Christina Pistone, is that this was predicted by Budiko, a Russian meteorologist, and Sellers in 1969. They said, when you warm the planet, the sea ice is going to melt. The sea ice reflects about 50 to 80% of the sunlight back to space. But when you blow the sea ice away, expose the darker ocean, the ocean absorbs 95% of the heat. So that's another feedback the system is having. And we were one of the first to determine that. And what we found, the models were under-predicting by a factor of 2. Okay? So contrary to what people say, oh, models are exaggerating, they're really under-predicting. So let me just now quickly wrap. Was that 10 minutes or 5 minutes? 5, okay. I'll rush. So I already the left side is what's maintaining the present climate. The middle is what the human blanket and mirrors are doing. And the right is how does the system get back, okay? It can radiate 1.9, but the ice feedback is cutting 0.3, so it can only give 1.6 watts. I am putting human blanket 4 watts, okay? And there are other feedbacks which I picked up from models, another 0.3. So what the planet can get rid of is only 1.3 watts per degree warming. We have made the blanket 4 watts. That's been measured, which means if there was nothing else, the planet has to warm 3 degrees Kelvin, Celsius or Kelvin, which by most standards would be catastrophic warming for the planet. And the reason we have not seen the 3-degree warming, of course, the ocean thermal inertia, but the reason is the mask, okay? And that's why I'm going to urge, we have some of the best experts in this aerosols in today's the rest of the talks. You just have to help us refine that number. Because just imagine you change it by 0.3 watts, that's 1/4 degree warming. So I'm claiming, I'm going to show you one more slide. I'm going to skip this. This shows why we have this weather extremes. But after lunch, I may come back here and talk about this. You can come and listen to me. So now let me go to this, my second prediction. We predicted 2018 when the UN was claiming you're not going to see the 1.5 degree warming in 2045. We used all the observed data in the energy balance model, and we predicted it's going to happen at 2030. Okay, you can see that 2025 the planet is already at 1.5. That's only 2 years, but it has to continue. And you see the rate of acceleration. We are saying the planet climate is accelerating. We were not the first to say that. I think Gunnar and Norman Loeb, several others have suggested this. The reason the planet's warming is accelerating at 0.34 degrees per decade, before it was 0.2, it increased 70% in 15 years. And we are suggesting, and we were able to predict it. This is a work jointly done with Yang Shu, my former student. He's a professor at Texas A&M, just using that simple equation, okay? And we are finding, why is it accelerating? We are not thinning the blanket, but we are thinning the mask. We are getting rid of the mirrors, okay? So I think the aerosol issue has become the foremost in predicting future climate. So Kim, we need your help. Yes, there are many, Gunnar. We just need to get the aerosol story and then the aerosol cloud interaction. We're going to hear from Sandrine Boni, one of the leading experts, and Frida. So I want to put some pressure on the 6 of you speakers. You can solve this problem for us and save the planet. Okay? And this is the last thing I want to say, and then I'll go on to finishing my stuff. Just a little bit gotten too complicated. We are able to predict the Earth energy imbalance. This was done just in the last 2 months by Professor Yang Shu. Are you here? Yeah, he was supposed to be here. Maybe he was, oh, there he is. See, the Earth energy, that's the dashed line is a theory. And the bottom line is the data. It's the same satellite radiation budget data that measures the energy imbalance. Yang was able to use the theory to predict, see the dashed black line and the red line. To me, after the 2 predictions I showed, it's one of the most convincing things. The planet does, climate does depend on these 2 variables. We better measure them. And the attribution is where the chemists, the physicists, and everybody comes in. So I want to conclude with this. you can, that the theory has passed critical tests. The theory is based on fundamental principles, okay? But there is a Gordian knot, and which is, if you ask me, is the warmer planet less or more cloudy? I don't know the answer to that. We don't even know the sign. So far, our data indicates clouds are not playing a big role. But we can't assure that it's going to happen, because once you cross 1.5, you maybe you're going to a nonlinear regime. The problem with the cloud feedback, if the storm track clouds or the stratocumulus just decrease by 2%, that's enough to double the warming. So that's what you can say. It also has possibility to halve the warming. I have grandchildren, children. Are you going to risk the future of billions just on this? Or take the safer route? We don't know the answer to the cloud. So you can use this, say, oh, these guys don't even know how the way the clouds are changing. Why should we trust the theory? But we have 30 years of data showing the clouds are not playing such a big role. But we can't be sure of that, okay? So this has already been shown. Our new approach is that so far 95% of our efforts goes to mitigation, cutting down the emissions. We have not succeeded. They're going up, okay? So it's time to protect the people. Where I come from in California, my biggest worry is that none of our houses are going to be insurable from fires, droughts. People like me, thanks to our vice chancellors and others, I'm paid well. I'm on retirement. I'm thinking of the people who are between 30 to 45 years old. And if their house burns or their houses are not insured, I don't see what future. So we have to think about adaptation. And on the last is societal transformation. We as a society, there are so many solutions. That's why I'm optimistic we're going to solve the problem. Our ozone moment will come when we cross the 1.5 degrees, 2030. And I think we will take actions, but I just want to make sure that we put enough funds into adaptation, how to protect people. Cutting down emissions, the ocean has a memory of 15 years. The temperature is not going to come down quick. It's going to keep going up, at least up to 2050. I'm predicting we will cross 2 degrees using this energy balance theory because of the unmasking. We are not thinning the blanket, we are thinning the mirrors. I have numerous thanks. I start with my wife and all of you here. You play a huge, huge role in my life. Thank you so much, and thank you, Crafoord Foundation. I want to assure the foundation and the committee that I plan to use the forum this Crafoord Prize gives me and the financial thing on creating this new structure. And my personal goal is to create 1 million climate warriors amongst the young. Thank you.